So it's now 11 o'clock, and I'm going to say welcome to the 22nd uh, episode of Covalent Academy. We're going to cover a little bit of housekeeping and various things. Many of you, of course, have attended these before, but for somebody that's new, one, we will be recording this session. Up, not yet, back up one. We will be recording this section, and we will essentially, it will be available on what is called the Covalent Academy. And at the end of this webinar, we will tell you how you can get to the Covalent Academy. Questions and answers will be handled via the question and answer button, which should be available, Q&A, at the bottom of your screen. So we will not be taking them live, and everybody but the presenter will be on mute by the time we're all said and done. So today's topic is optimizing materials with TGA and DSC. Well, I'm not going to say their long names. Parth can say their long names, but in the interest of coming along, before we get into what I think you're going to find to be a very interesting topic, let me tell you a little bit about Covalent itself. So Covalent Metrology, we are a Silicon Valley-based analytical lab, and in fact, putting together platforms to deliver data analysis, and our job in life is to help you solve your problems. We basically try to do faster, better, cheaper, and all three at the same time. Our job in life is to help you solve your job in life and make life easier. We'll generate data if that's what you need. We'll help you analyze, and we'll help you do your DOEs as well. So to give you an idea how broad Covalent's reach is, this is just a quick view of the types of things we do and the types of analytical techniques we have in-house and also with our network partners. This is always changing as we add more and more to the internal capabilities, as well as we add expert partners. You can reach us, of course, at covalentmetrology.com. And one of the things you will see on there is you'll actually see the prices for everything that is there. So before we get into this webinar, I want to talk a little bit about our collaboration with TA and who is TA Instruments. So they're a global market leader in thermal analysis, thermophysical properties, microcalorimetry, rheology, a number of areas, very well known. They are part of, I don't know whether I'm supposed to say a division of Waters or part of the Waters group, or I never did quite get this clear, but I mean, they are part of Waters, and as you can see, very wide range of materials and companies. So if we look at what TA can actually do and go, they offer a number of characterization solutions, and we're going to talk about the first two on this list, DSC and TGA. As you can see, there are many more, and I expect that we will have more webinars in the future that talk about some of these other techniques. You could spend days talking about any one of these. And in fact, there are courses, short courses offered on a number of these techniques. One of which I think is going to actually be hosted at Covalent. I'm probably stealing somebody else's announcement time, but what can I say? So Covalent is actually in the process of putting in both a DSC and a TGA from TA Instruments. So we find that this webinar is very timely in where it is and what we're going to talk about. So now, basically, it's my great pleasure, there we go, to introduce Parth. And Parth basically is an applications engineer, applications scientist, I think is probably a better way to talk about him, with TA Instruments. Got his bachelor's degree from the University of Toronto, very near where I did my bachelor's degree, which was in Waterloo. He got a PhD in material chemistry from Florida State. He's been working with TA for about 2.5 years, and I think you will find that very knowledgeable in what he does and very good at relating what these systems do to what you actually need them to do. And with that, I'm going to say, I'll tell you to sit back and relax and enjoy what I think is be a very good webinar. And I'll pick it back up at the end, at the other end. On to you, Parth.
Thank you so much, Chris, and good morning, good afternoon, or good evening to all of you attending. Today's talk, we will talk about DSC and TGA, and I've broken this talk into two parts. So let's start off first with DSC. So DSC basically, stands for differential scanning calorimetry, or the instrument would be called a differential scanning calorimeter. And so let's talk about what this is and what it can do for you. So one thing I should point out is the DSC that Covalent has is the top of the line DSC 2500 instrument. And this is attached with a cooler called an RCS 90 that allows you to do experiments down to negative 90 degrees Celsius. And we're happy to have Covalent using our systems. So to talk about what DSC is, I just want to say that it comes from the name. You can see that the name says differential scanning calorimetry, which means that we're measuring a difference in the heat flow between a sample side and a reference side. So in a DSC, like a heat flux DSC that we are talking about, we have a silver cell that has two pedestals for the sample and the reference side. We place a small sample into a pan, which is then placed on the sample side. We have a reference empty pan, and then the instrument heats and cools the cell and observes the change in heat flow coming due to changes taking place in the sample. So when we think about the heat flow, you can think of it as being comprised of the thermodynamic component as well as the kinetic component of the properties of the material. And the instrument can give you insights into things like the glass transition, crystallization, level of cure, any denaturation or decomposition that is associated with a heat-based signal. And a heat-based signal is universal. So when you think about a DSC, the types of data that you typically look at are plotted on a curve where you will see temperature typically along the x-axis, and then what we call normalized heat flow on the y-axis. And the graphs that you see will show you peaks and valleys. So depending on nomenclature, you can see that we have exotherms facing upwards. What that means is whenever you see a peak that is pointing upwards, that means that the sample is releasing heat. And this could occur for a number of reasons as listed over here. And on the other hand, if you have a peak facing downwards on this graph, that would be corresponding to an endothermic event, such as a melt or certain types of transitions, or when a liquid or solvent vaporizes and takes heat as the sample is being heated through. So a DSC is a really powerful instrument, gives you a lot of insight into things that are happening in your material. It gives you insight into characterizing it. And why do people use this? So I like to think of instruments and analytical methods in the structure, property, function relationship frame of mind. And so when you have a material with different chemistries undergoing different processing conditions, storage conditions, formula optimizations, that all affects the material in a way that can be detected by a DSC. And you do that by measuring the heat flow and transitions that show up in the measurement. And then that can help you predict how the material is going to behave when it's applied. It'll give you insight into how the formulation is affecting the properties of the material, and eventually how stable and compatible is this material going to be in its final usage. So a really powerful instrument. And not only do you have a DSC instrument, but you have certain things that go along with the DSC instrument. So for example, the RCS 90 we talked about is a cooling system that allows you to cool down samples to lower temperatures. You can also heat up samples to high temperatures. Typically in a DSC, we don't like to decompose the sample. And typically in most DSC experiments, we run samples under an inert gas like nitrogen. Sometimes you may use air or oxygen if you're trying to do an oxidative type of study. And we'll talk about TGAs as well, where you can do this type of oxidative study. And then when it comes to DSCs, we also think about the different types of pans into which we place samples. So at TA Instruments, we offer different types of pans that can be compatible with certain types of materials. And they also allow you to maybe prevent vaporization of a certain liquid, or allow you to put a pinhole lid, which allows you to do certain types of experiments that are different from when a sample is hermetically sealed. So those are some of the basics of a DSC instrument and some of the other components that go with it. And when we think about the DSC 2500 technology that is offered with TA Instruments, we have what we call T0 patented technology. So what this technology does is we reduce any assumptions we're making about what is the contribution coming from the analytical instrument itself in the heat flow values that you're seeing for your sample. And the way we do that is we introduce a third sensor in the DSC cell, which then helps calibrate out any differences between the sample side and the reference side during the age of operation of that instrument. And so you can always be confident that the values you're getting from the instrument are reflective highly of the sample. And then with the DSC 2500, there's also what we call a pan correction factor that takes into account any pan resistance that could be at play. And we basically do not want to assume anything when we have such a good instrument. And so the benefit of having such a good instrument clearly shows up in things like the DSC baseline, which some of you may or may not have heard of. And so what you're seeing in this baseline is that it's a really flat baseline across, -90 all the way to 400 degrees Celsius, the most typical temperature ranges for a lot of polymer chemistry work in the DSC. And the important thing to note in this baseline that I'm showing you, coming from a verification result on the instrument, is that the heat flow signal is on the order of 10 to 20 microwatts. And typically what you'll see in a sample, the heat flow coming from a sample is above 0.1, typically between 0.1 milliwatts to 10 milliwatts. So this is telling you that the baseline of the instrument's really flat. The data you can get is amazing, and you can pick up really weak transitions that you could not achieve if you did not have a DSC that had such a flat baseline or basically zero contribution to the heat flow. The other advantage of our patented T0 technology is that when you are working with materials that may have transitions that are close by, you get improved resolution. So this graph that I'm pointing at right now is basically what happens when you look at the endotherm of the melting of indium metal, which is typically used as a calibration material for DSC systems. And what you see is that when you go into the T0 technology, which is the T4 technology, and when you include that pan correction factor, what you're seeing for the endotherm for indium is that the peak is getting narrower and sharper as we would expect for the melt of a metal. And so you can see that experimentally with a high-end instrument, you can find out differences between two peaks that may be close by. And so you have more success of picking out things with a good DSC system. And so that's the advantage of having an instrument like the DSC 2500 at Covalent. So let's look at some example data that explains to you what DSC data gives you insight into. And typically, plastics are found in almost every type of system we work with. We talk about composite systems. They use some type of plastic or polymer, I would say. And here's an example of PLA. And what we're looking at in this graph is basically a heat and a cool cycle applied to this polymer in the DSC. And so what you can see from the information in the DSC is that when the sample is cold, this PLA is a solid, rigid, amorphous structure. And upon heating, it first undergoes a glass transition, which you pick up as a step. And we can see a small peak that is called an enthalpic recovery related peak. And then after the glass transition, the material transfers into the rubbery amorphous phase. And after that, sometimes, at least in the case for PLA, you can see that there is a crystallization peak that shows up as an exotherm. And after that, you could say that the material is now at a solid crystalline state. And following that, there's an immediate melt of PLA. And you can pick up the melting of that PLA with an endotherm. And then the PLA is now a liquid at 175 degrees. And then upon cooling the PLA, depending on the cooling rate that you apply on the DSC, you can see that in this example, using a cooling rate of 10 C per minute basically causes this PLA to go straight into its amorphous phase. And you can see that glass transition, being a reproducible feature on heating and cooling, again shows up on the cooling curve. So this slide, while it's a simple slide, sort of covers all the different things you can see in a DSC. And when you change the formulation or you have different polymers, these graphs or fingerprints are going to change. So people use this to look at quality control, to look at, improvement of formulations, to look at what point does the TG take place so that you don't want to use the material above or below the TG in certain applications. So I hope that this slide conveys a lot of information to you for DSC. And then here's an example of something like an epoxy that is cured and undergoing what we call heat-cool heat cycles that typically people do on DSC. So what you're seeing in this graph is on the first heat of this epoxy sample, you can see that you see a really sharp endotherm-like feature. And then we are seeing an exotherm that is related to energy released due to the curing of this epoxy. This could either be residual cure or, first-time cure. And then after that exotherm takes place, we cool this epoxy down. And when we're cooling it down, we see a nice clean glass transition. And then upon the second heat, which is of interest to a lot of people, we see that that glass transition is showing up clearly in the area of this endotherm. And so this glass transition gives you insight into the TG of this epoxy. And then you also notice that there is no exotherm on the second heat. This means that there is no residual cure left for this epoxy. And you can see that the heat flow curve is nice and flat. So fully cured material should not show you an exotherm. So going back to this endotherm peak is basically related to enthalpic relaxation. So the longer the material is stored below its TG, the stronger this enthalpic relaxation peak can become. And sometimes it can mask the TG. So a second heat reveals the TG. Sometimes you can run modulated DSC, which we'll talk about, in order to pick up the TG on the first heat. So when it comes to epoxies as well, a DSC can be used to do some quantitative measurements. So the TG is a quantitative measurement, gives you a value for temperature, but something that a DSC is also used for is calculating the percent cure. So let's say you have a epoxy and it's not cured at all. You run it on the DSC, capture the entire exotherm, find out the total enthalpy related to the curing of this epoxy. And we get this number for 10.6. Let's say we have an epoxy sample that was cured for 17 hours at room temperature. We take that sample, place it in a DSC pan, run it on the DSC, and look at what we see. And what we see in this sample is we see a glass transition followed by a small exotherm. So this exotherm is related to any material in that epoxy that hadn't fully cured. So by knowing the amount of energy for the uncured portion and knowing the total enthalpy you should expect for a fully cured epoxy sample, you can calculate out the percent cure. And so the DSC can be used to calculate the level of cure in an epoxy sample. And this is the goal for this slide. So with that, I want to switch over to something called modulated DSC. So this is basically a technique that can be applied on a DSC instrument. And modulated DSC basically is a method that was developed by TA a long time ago. And what this technique does is it helps separate out that thermodynamic heat flow that we were talking about from the kinetic heat flow. And so what this does is it allows you to basically get two signals instead of just one heat flow signal like we saw on previous slides. But what you get is a reversing heat flow signal and a non-reversing heat flow signal. The reversing heat flow signal is where you can get the TG that is being masked by something like enthalpic recovery that we saw on the previous slide. And modulated DSC technique is also used to measure the heat capacity of materials as well. So those are some of the big reasons why modulated DSC is used, and it can be run on the 2500 instrument that's present at Covalent as well. So the way modulated DSC differs from regular DSC is that you're actually modulating the temperature instead of just heating the sample at a certain linear heating rate. And you can do this on cooling as well, which a lot of people do not know. But by modulating the temperature, what we're doing is we're subjecting the sample to a modulated temperature, which allows us to then calculate out this term from this term. We have application notes on our website for any of you interested in learning more details about this. But what you get from a modulated experiment, which I'm showing you on this slide, is that if you look at the raw signals, we're looking at temperature, modulated temperature, time, and then the sample produces a modulated heat flow. This modulated heat flow is analyzed by the software to give you some of these curves, including the total heat flow curve, which is this curve in the middle. That just looks like your regular DSC run, but you also get what we call the reversing heat flow curve over here, and then the non-reversing heat flow curve. And what you can do with the information from modulated DSC is you can get a lot of insight into materials that are hard to analyze. And so the reason why you would run a modulated DSC, and before we talk about that, is that in a material, typically you always want to run a regular DSC experiment, which is typically 10 to 20 C per minute. And then let's say you have overlapping transitions, or you cannot really see the TG clearly, then you may consider using modulated DSC. Or for those of you who are interested in getting the most accurate quantification of polymer crystallinity in a sample, you can use modulated DSC. And there's a lot more reasons to use modulated DSC. So when we look at the data that comes processed in the software after it analyzes it, what you can see is that if you look at the total heat flow curve here, you can see that the TG is showing up, but we also have a little bit of an endotherm. With modulated DSC, we separate out that endotherm as the enthalpic recovery on the non-reversing heat flow. And on the reversing heat flow curve, we can see a nice clean glass transition. And then you can see that something like cold crystallization that takes place in a polymer is a kinetic process that is captured in the non-reversing heat flow and absent in the reversing heat flow. And then for certain types of samples, what you'll find is that the onset of melting in the regular DSC run shows up at a higher temperature, but it really starts off at a much lower temperature, which you can pick up with modulated DSC. And the reason why you can't see it in a regular DSC run is because that melting is being masked by what we call crystalline perfection that is taking place in the sample. And so that is an exotherm that you're seeing that couples up with the melting heat flow and masks the true onset of melting for the sample. And so modulated DSC is a really powerful technique used by a lot of people. And an example of modulated DSC that I have time to show you in this talk is an example of, again, an epoxy sample. So what you see is that if we ran a regular DSC run, you would see that the total heat flow looks like this. You just have a flat line followed by an exotherm related to the cure, and then an exotherm related to potentially decomposition of this epoxy. But when you run this sample under modulated DSC, what you can see is you can separate out the reversing and non-reversing heat flow curves, and you can easily pick up the glass transition on the modulated reversing heat flow signal and capture all the exotherm on the non-reversing heat flow curve. And so it's a really powerful technique for complex systems. So with that, we are going to actually switch over gears to TGA. And maybe the one extra learning point I can put in here is that modulated DSC is a technique that's a little bit slower. And typically we run them at 2 to 3 C per minute in order to be able to let the sample modulate along with the temperature. So it's a slower technique, but a more powerful one. Sometimes eliminates the need to do heat-cool heat experiments. And you can just do one single heat and get the data. So with that, let's switch gears into thermogravimetric analysis, or TGA. We call these instruments TGAs, where you would change analysis to analyzers. And these instruments are very powerful, ubiquitous in a lot of places. And Covalent Metrology also has a TGA 5500 instrument. And I believe theirs is coupled up to an FDIR to do evolved gas analysis as well. So this instrument, like the DSC 2500, has an autosampler, so really high throughput analysis, and really important technique for a lot of materials characterization. So what is TGA? So simple way of me explaining what TGA is that you can think of it as a really, really fancy balance being placed into a furnace, and then watching how the sample loses mass. So on a TGA, you're basically looking at change in mass in the sample as a function of temperature, time, and also atmosphere. And the way we can achieve that is because the TGA instrument has a couple of gas ports in the back. And the way it works for TA Instruments is that we have a gas 1 port connected to nitrogen that delivers an inert purge gas of nitrogen that goes through the balance to keep the balance operational throughout a long period of time and high temperatures. And that purge gas then blows onto the sample. We also have a gas 2 port that is typically set up with air that customers choose or oxygen. That allows you to introduce air over the sample when you're trying to oxidize a sample. And this balance housing on the top uses a vertical balance principle with an electronic system that makes sure this balance stays horizontal upon loss of mass on the sample site. And this furnace basically mechanically moves up and down. And when you're running an experiment, it's raised up and it heats up the sample that is placed in a pan, typically aluminum pans, but platinum pans, but we also have alumina pans that allow you to run certain types of samples not compatible with platinum. So the reason why people use a TGA, again, going back to the structure function property relationship, a TGA also can give you insight into the structure of a material, give you insight into the composition of a material, and give you insight into how stable the system is going to be upon heating. So by testing samples that come from different chemistries, different type of processing conditions, let's say you have any residues left or stored in certain humid environments, for example, you might be able to deduce some of that from a TGA instrument, because the TGA instrument not only gives you information about how thermally stable it is, it can give you insight into composition. You can actually do some kinetics analysis on the TGA, and we'll talk about this at the end. And you can also change certain types of gases that can be introduced onto the TGA and look at the content of residues that is left over at the end of a TGA experiment, as well as the amount of moisture or volatiles that are present in your final product. And this is important because it helps you understand things like volatile organic content that is left over. And one of the examples that my colleagues at TA have told me, whenever you step into a new car, you think about, oh, the nice leather seats smell really good. That is actually some volatile organic contents that are still, coming off the car. And so, they have to manufacture them so that there's not a very high level that can be harmful to human health. And when you do kinetics, you can understand what's the lifetime. So let's say you have a polymer that is being used as an insulator on electrical cables. You have to understand how frequent, or in terms of years, do you need to change out that insulation before it may cause a fire. And it also gives you insight into the chemistry of your new compound that you have developed. So a sample can lose mass because of solvents evaporating or boiling off of the sample. You can have decomposition. So certain polymers, once you get above a certain temperature, they're going to start decomposing because you're breaking the bonds between, the carbon atoms or all the atoms in the polymer system. And then sometimes you can have oxidation or corrosion. So when you think about a metal, if you expose it to air at higher temperatures, kinetics kicks in and the metal oxidizes really fast. And sometimes you can add oxygen to your sample, so you may see a mass gain. And the important thing about a TGA is that everything is kinetic. So you can actually look at the effects of testing a powder versus a pellet, and that's going to behave differently in terms of temperature in the TGA as well. So a lot of useful information that comes from a TGA, and therefore they're so ubiquitous. So let's talk a little bit more about how do you prep a sample before I show you what a real TGA curve looks like. So on the TGA, I mentioned you can use a platinum or a ceramic pan. This hangs from a hang down wire connected to the balance. We typically like to spread out the sample, typically between 10 to 20 milligrams for most applications, unless you're looking for residues. And therefore you would bump up the mass if you're looking for residues, because we want to make sure that whatever residue is left at the end is above what we call the baseline noise of the instrument. And with an instrument like the TGA 5500, we're talking about a baseline drift of less than 10 micrograms. What that means is when you heat up the sample from room temperature to 1,000 degrees, the empty pan does not show you a big change in mass. What that means is that if you have a sample and you have a residue of very few percentages, as long as you tune the sample mass to the right amount, you will make sure that you are getting an accurate value for the residues. And the nice thing about our instruments, both the DSC and the TGA, is that because we have such beautiful flat baselines, we do not do any baseline subtraction or post-analysis on the samples. What you see on the instrument is a signal coming from your sample. And here's an example of a well-maintained TGA 5500 instrument, and you can see across the temperature range, you barely have 1 microgram of drift. So really, really sensitive TGA system. So let's look at some data on what you get from a TGA instrument. So what you're seeing over here is 2 curves related to PET. One's an amorphous sample, one's a crystalline sample. And what we see in a typical TGA graph is we have temperature on the x-axis, or sometimes you may have time if you're just holding the sample at a certain temperature. And on the y-axis, we always look at weight percent. You can look at the raw weight itself, but weight percent allows you to compare different samples because you have normalized it to the initial mass of the sample. And what you can see is that in the TGA, for example, between an amorphous and crystalline crystalline structures are supposed to be mechanically stronger from my experience in the world of DMA. And what you can see here is on the TGA also, when we look at the weight loss of this PET, basically when it starts to decompose, we're seeing almost a 5-degree difference between crystalline and amorphous PET for the onset of decomposition. And this basically gives you insight on, how amorphous or crystalline the sample is, with crystalline materials showing a higher level of temperature stability. So that's one example of how you can use a TGA. Another example is oxidative stability. I mentioned you can use different gases on the TGA. So let's say you run an experiment on this polypropylene resin purely in air. What you observe is that in air, this sample actually degrades a lot faster at a lower temperature at 285 degrees. But if you ran that sample in nitrogen, polypropylene is nice and stable, almost till 430 degrees. So you can look at the effects of the environment using a TGA system, as shown as in this graph. And you can make it a little bit fancier by doing what we call a gas switch experiments. So what you are seeing on this graph is an overlay of different polymers that have been run on the TGA instrument. And what we did in this experiment is we ran all these samples to 650 degrees at 20 C per minute under nitrogen gas conditions. And then once the samples reached 650 degrees, the instrument basically introduces air. And when you introduce air at a high temperature, anything that is decomposed and carbon-like is going to start reacting with oxygen to produce CO2 and CO. So you basically burn off any carbons at higher temperatures once you do a gas switch. And so by doing these types of experiments, you can see how different polymers show you different profiles in the TGA, different onset temperatures for degradation. And once you do the gas switch, you can see what is the final level of carbon that is left. In this case, you can see all these polymers go down to basically 0% weight at the end of the experiment. But let's say you had a filler, which I'm going to show you in the next slide. You can see the amount of filler that is left, such as silica. So TGA is really powerful, gives you a lot of insight into how materials decompose. So here's an example of a more complex system run on a TGA. We have basically a composite that contains PTFE and silica, and maybe it has some carbon filler, but that'll be a topic for a different day. So what you can see is that this sample was run in a TGA, 10 milligrams at 5 C per minute under nitrogen. We heat it from room temperature. As it's heating up, we can see that there's a small weight change corresponding to volatiles that are coming off of the material. And then once we get to a high enough temperature, we start to see the PTFE is degrading. And then when we apply that gas switch to air, we burn off any carbon that's present in the sample and from the PTFE. And what we're left with at the end for the weight percent is the amount of silica that is in the sample. And so you can see that the residue corresponds to basically that of the inert filler in that material, which is silica. So here's an example of how TGA can be used to analyze composite systems. And then now we'll talk about what is high resolution TGA. This is basically a method that we provide on our TGA instruments, including the 5500, where the instrument and the software automatically control the heating rate based on how fast the material is decomposing. And so the way it works is, think about you being on a road. When there's no traffic, you can follow the speed limit. As soon as you hit traffic or an accident, you have to slow down until you're cleared of that traffic region. And so that's what the TGA basically does in that experiment. And what we're looking at in this graph is 2 runs. Let's focus on the standard TGA run. This is basically an experiment where the TGA is run at 10 C per minute. We basically are heating this polyurethane sample and watching the weight loss. Not only do we look at the weight loss curve, but typically in TGA experiments, we also like to look at the derivative of the weight percent as a function of temperature. So a lot of people will use these peaks to look at where the maximum weight loss is taking place, which obviously corresponds to the degradation of the sample. And so in a standard TGA experiment, sometimes you may not be able to resolve 2 weight loss steps as clearly, either looking at the weight percent spectra or looking at the derivative. You can see that these peaks are not as well defined as the run using high resolution TGA. So in this experiment, the instrument is allowed to go up to 50 C per minute, but is allowed to slow down to almost, I believe, 0.5 to 1 C per minute. It doesn't go down to 0, but it comes down to such a slow heating rate where basically weight loss steps appear a lot more vertical. And therefore the derivative peaks appear much more sharper. You can resolve peaks a lot more cleanly using high resolution TGA. So it is a method that gives you better resolution and sometimes faster run times, or a little bit of compromise in time to achieve resolution that you cannot achieve using a regular TGA experiment set up on the TGA instrument. And then the last thing we'll talk about, or the 2 last things we're going to talk about, is TGA kinetics. So we talked about how one can look at, insulating polymer or rubber, something that is preventing electrical cables from, short circuiting each other. You could estimate the decomposition of that insulation by using a TGA. And the way you do that is, and we'll talk about that, but the way you do that is you basically are looking at the decomposition of the material at different temperatures. You're trying to apply Arrhenius kinetics to get an activation energy for decomposition, and then try to predict how long is this material going to last as a function of temperature. So the higher the temperature that this material is being used at in its application, the shorter its lifetime. And so you can get certain predictive abilities when you do kinetic analysis on the TGA. And typically the way that is done, if you follow the ASTM method, is that you take a sample and you run multiple specimens of it at different heating rates, and you observe at what temperature does it lose a certain amount of mass. So in this case, we're talking about 10% weight loss or 10% conversion. You take that data, you basically fit it to a model, pull out the activation energy, and then you can predict lifetimes using this information. Another way you can do that with a TGA 5500 is by using modulated TGA. So this is a method similar to modulated DSC, where you modulate the temperature in the TGA, and in the area where the sample is decomposing, the instrument basically will analyze that data because it is subjecting the sample to different heating rates, and it'll give you a graph where you have the activation energy. And if we look at this value for activation energy for PDFE, it is 354, which is pretty close to what we saw using the ASTM method. So modulated TGA, is a method that reduces the need to run more than one specimen. And in one experiment, you pretty much get the activation energy on your TGA data. And so you can use this to then predict lifetimes. And then to close up for this quick but insightful seminar, I want to talk about what else you can do with the TGA. So TGA instruments can sometimes be connected to other instruments to do evolved gas analysis. So what I mean by that is you could take up a TGA and hook it up to a gas cell FTIR system or a GCMS system, or both. And at Covalent, they have our TGA hooked up to an FTIR, which allows them to look at the FTIR analysis of the off-gassing products. So whatever is decomposing into its gaseous form and coming off of the TGA is collected by an FTIR, and then you can get an analysis of what that is. So here is an example of PPO, and this was run on the TGA. And when you do TGA FTIR, you get what we call a Gram-Schmidt profile. This profile is then, when you click on each point, gives you information of the FTIR spectra that is being read by the FTIR instrument. So this way you can get a lot more insight connecting the TGA to an FTIR. And with that, I will say thank you for attending and for giving me the opportunity to talk Covalent, and I'll pass it over to Chris now.
Thank you, Parth. I mean, it was, I always find these interesting, and I always learn something new each day. And in particular for this one. So we are going to do question and answers in a second, but we have a little more housekeeping to keep up with. So you can move to the next slide for me. So our next webinar will be on nano indentation with a new step 6 platform. This is a tool from Anton Parr, which has recently come into Covalent. And there'll be more details to come on that. So please watch us and watch our LinkedIn, and we'll give you more information as it's available. Next slide, please. So we talked a little bit about the Academy, and basically to get to the Academy, there are a couple of things can happen. You can go to the Covalent Metrology website, and you'll notice that there's a login button up in, or a login thing up in the top right. It is not circled in yellow, and it does not look like this. It just looks like a standard thing. This is just to point out where it is. And in a sec, we're going to talk about what happens when you push it. But before that, I'm going to make one plug, which is if you've not tried the search engine on the Covalent website, I would recommend that you do. There's been a lot of work put into it, and it is getting to be awfully good at helping you to find out some of the things that you need. Now, after that, next slide, please. So if you press the login button, you're going to see that basically there are two ways to get at the community. If you're already a Covalent customer and you run on our normal data portal, you can sign in just like you would normally to get your data. And you will notice that on the left-hand side, down near the bottom of the menu, there is in fact a Covalent Academy sign in that you can use. If you're not a member of Covalent's data portal, then in fact, you can go to the right-hand side and develop a login for the Academy portal itself. Pretty straightforward, not the same level of security, so you don't have to go through quite as many things. The issue when you come down to it becomes that now all of the recordings of all 22 webinars will be up there. This one will be up there, probably end of this week or beginning of next week, plus the slide set, plus the question and answer session that we'll get into will all be there. We view this as a resource for the community at large, not only for our users, but for the people that attend what I think are these excellent webinars. Next slide, please. So now we're going to go into the question and answer session, and this is where I get to have fun because Parth doesn't know what I'm going to ask him. Some of these questions have come from some of the people. Some of these questions essentially are ones that intrigue me as I'm going through. So let's start with a couple that make maybe a little more sense. So I did notice that you looked and did the poll. I am sorry, Shannon. Please also up on your screen should have popped a poll. If you would please answer it. It helps us actually work through how to make the webinars better and how to serve your needs as well. So I'll apologize for that. You can answer that while we're doing the questions and answers. So one of one of the questions we got is how reproducible is a TGA when we're looking at it? It doesn't look like it has active cooling, so I guess it's a one-way street in many ways, or is there active cooling on it? And also, in in conjunction with that, we often will have material come in that where a customer says, I think it's this particular polymer or that particular polymer. I assuming we can use a DSC or a TGA to actually determine what it actually is. Are there libraries of where these melting points should be, or where the crystallization or what the curves look like?
Great questions, Chris. Let me just write down these couple of bullet points. I remember what I need to answer. So library. So with regards to the TGA, typically a TGA is an instrument that is used for heating only. We typically do not do cooling with these instruments. It does have a cooling gas port that allows the furnace to be brought back down to room temperature really quickly. So for example, with the 5500 IR furnace, it's a small volume furnace that cools down in less than 20 minutes back to room temperature. In terms of reproducibility, very reproducible. We run TGA samples here at our demo lab, and the goal for reproducibility, like I mentioned, the TGA is a kinetic based process, or losses, thermal loss due to heating is a kinetic process. So for reproducibility, we always recommend that when the TGA is run, you want to try and keep the sample masses the same. You want to keep the morphology the same. Like I mentioned, if you run a powder versus a pellet, you may see differences because the ability of a powder to heat up versus a pellet by the time the interior heats up, it can differ a little bit. But I will say that if you're in the same sample masses, you run the same experiment, if you run one at 20C versus 10C, you may see a little bit of shifts because it is a kinetic based event. But if I run the same sample 10 times using the TGA with the same conditions, same sample mass, pretty much you should be almost dead on, right on top. The curves are typically right on top of each other. So very reproducible. You typically do heat only experiments on a TGA. When it comes to the DSC, you are right that when you have an unknown sample, typically, different polymers will have a signature, you could call it, on the DSC. So the glass transitions, the enthalpies for their melts, are sometimes very common. We do not currently have a library, and that is one of the things we sometimes explain to customers, that the library, yes, you can run a polymer sample and you can see what its profile looks like, but coming from the world of TA Instruments and I guess things that are in my head, when you think about the processing that a material has undergone or the kinds of storage conditions, you can sometimes see a clean TG, or you'll see a TG with what you call enthalpic recovery. Processing and crystallinity, all these factors can shift the positions for some of these features that you may see on a DSC. So at the moment, we don't really have a library, but a customer can always buy a certain polymer and run it to characterize it. But to be aware that things can change the polymer over time. So you should sort of look at information in literature, and you'll also see in literature and information from suppliers that they do have different grades, they have different processing conditions, and that's where you want to confirm the information on the DSC. But do not believe always that if the TG is supposed to be 55, it'll never move away from 55. Sometimes it may move up to 60, it may move down to 50. It also depends on the thermal history of the sample.
Okay, relatively complex. I gave you a complicated question and you gave me a very good answer. So often when you're looking at DSC data, you'll see a transient right at the beginning.
Yes.
Right. What is that?
That is typically what we call a startup hook. So when you are taking an instrument that is at ambient conditions or at a certain temperature, and now you're trying to accelerate at 20 C per minute, 10 C per minute, what you will see is that as the instrument is trying to get up to the heating rate, you will sometimes see a startup hook. And fun fact, the startup hook, because I mentioned the word accelerate, if you try and go at 5 C per minute, the startup hook magnitude is not as large as 20 C per minute. So that startup hook is not a feature coming from the sample. It is due to the instrument starting to accelerate. And typically what we recommend is if you're running a sample and you're trying to investigate the DSC nature between 25 and 200 degrees, I would say you always want to start the sample colder, or on the first heat cycle, start it at 25, go to 200, then cool down the sample to 0 degrees, and then do a second heat. Therefore, your startup hook isn't into play in your data that you achieve. But that is a startup hook. It is not from the sample.
Okay. So I have a question been asked about, can I use these tools to measure the boiling point of materials?
Great question. So the DSC is an instrument that sometimes people use to measure the boiling point of samples. If you do decide to do that, the goal is the DSC is an instrument that you do not want to contaminate with materials, because it's that same cell that you are running multiple samples in. And so when you do a boiling point experiment, you will typically use a hermetic lid. And we offer certain types of pans, such as these high volume stainless steel pans that can handle 40 atmospheres of pressure, go up to 250 degrees Celsius. So if you're trying to boil a material, you can use a DSC to do that, but you want to use a hermetic pan so you do not contaminate your DSC cell for other measurements. For TGA, typically when we look at the weight loss profile around lower temperatures, that is typically solvent coming off. I would say you probably will not use that for a boiling point, but you can observe when a material is starting to leave the sample. So water is going to evaporate even at 30 degrees if you give it long enough, if you've poured water, but if you have a surface at 100 degrees, that water is going to convert directly to steam right away. So I would not use a TGA to measure the boiling point, but I would use a DSC.
Hermetically sealed DSC.
Hermetically sealed.
So you don't mess up your cell, right?
Correct.
Yeah. So we have a question basically that they would like to look at the effects of moisture. So relative humidity, changes in relative humidity, maybe to do, I've seen it used in epoxy cure type measurements and things. So how would you use these tools to look at something like that?
So maybe just a little bit more clarification. Are you looking at samples that have been subjected to different relative humidity levels before running it on these instruments?
Yeah, I can't quite tell from the question, but I will give you my version of the question, which is I have a material and I want to look at the changes, how that material behaves as the relative humidity around it is changing.
I see. So, with the TGA, the gases that we typically use are dry gases. The TGA 5500 or the Discovery series of those instruments, they're not designed to look at weight loss in the presence of moisture. We do sell other types of instruments. We have what we call high pressure TGA systems. Those are instruments that can be used to introduce steam into a TGA system. For a DSC, you don't really control humidity on the DSC, but if you have a sample that's been subjected to different humidity, you can place it in the DSC and observe how it behaves, or whether the humidity has changed the glass transition. So, we have an example from our DMA slides where, nylon. On the DMA, we have a relative humidity chamber and on the rheometer, and you can observe how the TG actually shifts depending on how much moisture is in that nylon sample. Not TGA and DSC related, or maybe it is, because we sell another type of TGA called a Q5000 SA. It's basically a TGA that allows you to control humidity levels. You can step up or down in humidity, achieve a temperature range between, let's say, 5 to 85 degrees Celsius. That is a TGA designed to look at levels of humidity and effects of humidity by looking at changes in mass. So I would say that would be maybe a Q5000 SA type of instrument that we provide.
It never ceases to amaze me how many different types of instruments people can come up with and how many different types of measurements they can come up with as well. So the so you talked about modulated TGA, right? Now, I can understand modulated DSC because you have the ability to actively cool, so you can heat cool, heat cool. How do you do modulated TGA? What's the cooling mechanism on that side?
So from what I understand, and I may have to do a little bit more research to come up with the full answer later, but I believe that it either uses some of the cooling gas in order to cool down the sample a little bit, or it basically turns off or it slows down the heating so that the sample is sort of not continuing to heat up. So it basically uses a combination of those two, or one of those two, to sort of control the temperature.
Yeah, so in reality, what you're really doing is modulating the rate of change of temperature. That's
Correct.
probably more correct to say it that way.
Correct.
Okay, that makes sense to us. We're at 11:55, which is where we're going to close the question and answer. For those questions that we did not get to, we will put the entire question and answer session up on the Academy, Covalence community, and be available along with, as I said, the recording of this webinar, and also the slide set will be up there as well. For those that asked, will we send this out to participants? The answer is no, we will not. Normally, the way you can get at all of the Academy's recordings and episodes by basically just signing up. And we're not going to bother you with a lot of stuff. That we put this together as a service for the overall community. And basically, by joining it, you're not committing to anything for Covalent. I think it's a good investment and a good way to learn. Most of our instrument partners have looked at some of these at some points as they're looking at other types of things. There's just far too many types of measurements to be done to keep all of them in one place at one time and have you understand them. So we find the references quite helpful. Parth, I'd like to thank you. It was a very good webinar. I very much enjoyed it. I hope you enjoyed the question and answer session, which, like I said, you didn't know what I was going to ask. So these are the part of my fun in it. Thank you all for joining us. We hope to see you again when we go to episode 23. Stay tuned, and we will actually give you more information about that once it's further available. And have a good day.